So hello everybody, I'm going to talk now about the Bilbao project. So if you have never heard of it yet, you will hear all about it, all the details. So it's a project which was led by Unai Igartua, and it involved, yes, and the BELE school and the students. And
yes, we are at the school, but we have no students on Friday.
Ah, that's a pity. And it was funded by Erasmus Plus, and it has involved quite a lot of people. Here I've only put the people who were involved from the beginning to the end, but then many people got involved. You will see that external makers made some violins as well. So yes, so I just put the people who really participated at the core of it. So I'm dividing my talk in two parts. The first part is more about the construction of the violins, and I really invite Unai and Anders and Luis and George and Roberto to interrupt and complement when you feel it. And then the second part will be more about all the perceptual testing we have done and some results. So. Okay, so the goals of the study. Well, it was to gain understanding of how a single construction parameter, so here's the thickness, can affect the playability and the sound quality of an instrument. We wanted as well to better understand the matching or not of the thickness of the two plates of a violin. The idea, because it's Erasmus Plus, that means that it's not just research, it's actually a lot of training and educational in it. So it was to involve the students at BELE school in the project, which could offer them a training through a large-scale project. And the idea as well was to design the project in a way that some parts of it could actually be reused for another study or many other studies for studying other construction parameters, like for example, the density of the plates, or maybe even like changing the arching. So the benefits will be, of course, for the school, for the violin making community, and the violin acoustics research. So previous research, which is basically at the origin of the BELE school, it's Jesus Alonso Moral and Eric Janssen who have designed a study to investigate the influence of plate thickness in the 80s. They combine different tops, ribs, and backs, pliant, normal, and resistant, but they only made 3 violins at a time. So there were 12 combinations possible, but basically only 3 violins could exist at the same time. So that was one of the limitations, because you couldn't really compare all the violins all together. In addition, another limitation is the fact that the parameters they used were probably standard at that time, but not so standard anymore, with tops from 67 to 93 grams, ribs from 0.6 millimeter to 2.0 millimeter, and backs from 115 to 147 grams. We know that thick ribs don't work, that very thick backs also don't work. So, and in addition, the results were not so conclusive because they had many difficulties controlling all the variables. So that's the origin of the project, is to redesign the experiment in a way we can hopefully achieve more stronger conclusions and taking advantage of all the possibilities offered in the 21st century. So we've decided to build 6 violins. We will only combine what we call pliant, so medium and resistant tops with medium backs, and pliant, medium, and resistant backs with medium tops. So one plate is always medium, and the other plate can be thick, resistant, thin, pliant, or medium. Here in the middle, we have a medium. We decided to do it twice to check reproducibility. So to see whether the differences between 2 medium violins would be indeed smaller than the differences between a medium and a medium pliant, for example. Okay, because otherwise, without this control, we can expect that the differences are due to the difference in thickness, but we can't really be sure. So we really needed some control, because even if, as you will see, we will really try to minimize all the variables and control them as much as we can, it's not fully possible. We chose different standards because they are different today. So the tops were from 58 to 73 grams with base bar. The backs were from 87 to 115 grams. And the regular rib thickness of about 1.1 millimeter. So how to build a set of violins in a very, very highly controlled way. So it is very important in this project to maintain all the other variables than the one we want to study, which is the thickness, unaltered in all the violins. Because we know that the arching is probably the most important and this is variable in the tonal quality of the violin, we needed to have the same arching on all the violins. And this variable is of course very difficult to control if the violins are handmade. But today's technology allows us to get the same arching using CT scans and CNC routers, which is what we did, but not without problems. So first, of course, when you build a violin, you need to choose a wood. So this is a range of densities which are commonly used in violin making, with spruce between 320 and 470 kilo per cubic meter, and 500 and between 500 and 700 for maple. It is known that for the top, high density wood does not work acoustically, and that very low density is also not recommended. So we decided to choose a medium density spruce, most commonly used by violin makers today. It's not clear which maple density is best, but we decided to also choose medium density for maple. So it's not easy to find proper wood with a defined value of density, as you probably all know. For the tops, we chose half a log of PCA Aviles cut in 1995 and split in 9 contiguous wedges, from which we hoped to obtain a group of 6 very similar tops. So we had 9 and we were hoping to be able to find 6 which were as similar as possible. The density range of these wedges went from 370 to 390 kilo per cubic meter. For the backs, we decided to use 3 irregular logs of Acer pseudoplatanus, the most common used maple. And here the density range was between 570 and 590 kilo per cubic meters. I mean, it sounds easy here on the presentation, but I think you can ask George, Unai, and George that just actually choosing the wood and finding pieces were close enough was already a big job. Especially that in the process, some of the wood was ruined and we had to start all over again. So I was talking about density, well, but how to measure it accurately, and that had been quite a big deal. It's a challenge. So they've used 2 methods. The first method is the volume displacement method. Beware of taking into account as well the absorbed water by the wedge by comparing its weight before and after. And then they did the geometric measure as well. So the wedges needed to be planed to match the exact geometric shape. And of course, you have to be aware and take into account the weather conditions, which could affect the mass. And so that's why they used a closed cabinet with controlled moisture and temperature. And so they used this method as well for this. I mean, we can discuss afterwards. If you want more details, you can talk with George, Unai, and Roberto made the measurements. So this is what they found. So here we have the water displacement, the geometric measure for the 6 backs and the 6 tops. You can see that the 2 different measures don't necessarily agree. So sometimes pretty well, sometimes much less. So that gives us an estimate of the density and shows us that overall it's quite close for all the plates and quite close for all the backs and for all the tops, even if it's not fully identical. I can't see the chat. I can see it lighting up. So Tim, if you don't mind doing the chairman again and interrupt me if you see any questions that I should address right away.
Yes, people are discussing, but there are no relevant questions yet. Okay,
thanks. So then we had to choose the model and to compute it. So we decided to use a Stradivari model. This was a big discussion, what we should choose. But so they thought, well, because it's a training, there were many reasons. So the first reason is like throughout his professional life, he created violins with very consistent arching and outlines. So that was one reason. The other reason is because it was a training for the students at BELE. Of course, it was more attractive for them to work on a model which is famous than to work on any model. So that's why we chose this. Then we had to choose the violin itself, and we used the 1713 Huberman violins because we could get access to its CT scan data, which was made by Sam Sigmuntovich and so it was not in the medical scans, CT scans, which are quite precise. The scan slices have a resolution superior to 0.1 millimeter, but it's not easy to create and generate surface of the scan volume from those slices. All the more that all the instruments accumulate deformation and irregularities over time. So to which extent do we need to compensate for them when creating the arching model? For example, there was some thinking in the sound post area, which needed to be corrected. So the design was modified to restore and recreate the original arching that Stradivari did create when he actually made the violin.
George, you asked a question. He says, you mentioned that high density spruce doesn't work and that low density spruce also doesn't work. What would you characterize as low density spruce, and what happens if it is used in making a violin?
What I could low is below what we think is like low is here, 320, or probably maybe even lower. Then what would happen? That's not to me to ask, is to ask makers. I think when they say it's known that it doesn't work, I think that was based on experience.
Shall I try to answer that?
Yes, please.
Well, there comes, because the elastic modulus and hardness of the wood correlates with the density, there comes a point when the wood isn't really strong enough to sustain the forces, and things like bridge feet sink into the top. So as you get kind of, I mean, you can have wood at 0.32 or 320 that's perfectly okay to work with, but below that you can start to have problems. You know, you address another range of problems about how to work with it. And at the top end, you're forced towards to have thinner plates if you want any kind of depth and response. And there again, that's another problem, because you know when they get to be you know 1.5 millimeters thick, they also run into problems, and you're trapped in a corner of only one kind of sound. Whereas if you work in the middle range, there's a lot of things you can do with the wood. So the extreme ends are problematic and the middle is easier.
And the other complexity was that the fact that we really wanted a perfect finish. So the plates would only be graduated from inside to adjust the thickness. And so we needed an accuracy which is usually not achieved with regular CT scans. So when we generated the model, like some bumps, for example, appeared on the surface that needed to be flattened. And the problem was a bit like those bumps were not really evident in the routed samples. They were evident in the routed samples, as you can see here, but not so easy to see in the design computer models. So here we can see it now because we saw it. So basically there was a lot of like going back and forth, generating the model, then Roberto would actually cut the plate and then realize, oh no, it's not good, we have a bump there or there, and then they would go back to the model and try to modify it, and then Roberto would cut again. So there was a lot of wood spent into in cutting different plates. There is a problem as well of CNC routing the plates. Wood is not a stable material. The heat and the internal tensions make it move a lot when it's routed. So the routing strategy is very important. And even if we take care of the reference points quite accurately, it's not easy to maintain a precision of 1/10 of a millimeter. Once the outside arching is routed, we also need a negative surface to support the plate in order to route the inside arching.
Claudia, Sebastian asks, can you detail how the modifying of the model was done? Was it by hand or was it something algorithmic?
Yes, I mean, I have more slides about this at the end of the talk, but I don't want to lose the overall idea. So I will prefer to go back at the end, especially that this is the part where really I will not be able to talk about it. And I will really let George and Roberto and Unai to talk about it. Okay, but there are more slides. It's just here I want more to give like an overall picture of what are the different steps without necessarily going into a lot of details, just so people see the overall picture of the project, if that's okay. But yes, machines are not perfect and sometimes they do not follow what was intended. So a lot of wood wasted as well this way with bizarre things happening. But so in the end, it was a very, very long process. You may wonder why it was so long. So we will go back to some details at the end. I think that now, especially after having heard what Francesco is able to do now, probably some progress has been made as well, because that was in 2016, so 4 years ago. And so now there are probably mistakes would not be done again. But at that time, it was basically the first time where really we wanted to go from a scan to a perfectly finished product, basically. And so about 2 years later, after a lot of like, how do you call it? Sleepless nights, especially for Unai, the tops and backs arrived at BELE. Now they had to graduate the plates. Okay, so for this, they decided to use a specific impedance from Evan Davis formula, which take into account the mass and the frequencies of the free plates, modes 2 and 5. Okay, so you basically do a model analysis of the plates, get the frequency of mode 2, mode 5, put this in a formula, and you get impedance Z. And so they were basically using Z as a control parameter to decide how to graduate the plate. So here what you can see is we have 6 colors, that's the 6 plates, starting from a very, for a high weight to a smaller weight. So basically this was the original state just after being CNC routed. And then they were progressively graduated until for some of them arriving at this weight. So this is a process of graduation. Here is the impedance. So you can see here, there were already 3 or 4 plates which had kind of a very similar impedance to start with, but there were 1 plate which was already a bit different. Okay. So here what is original is the fact that using this impedance to actually graduate, to control the graduation process, and you can see that even the green one was even more, and decide which plate will be used for which purpose. So because this plate already started with a much lower impedance, it was decided that this plate would be the one which will be trimmed even more, graduated even more to become the thin plate, because it already started being different on the thin side. This one was different as well. So it was decided to keep it as a thick plate. And then the other 3, which were, the other 4, which were very similar, were decided to be kept as the medium plates. Okay, so this was a way to control, not just to control by actually doing what we would call static measurements, so just the weight and the profile, which was done by CNC, but actually using some modal analysis, and in particular the mode 2 and 5, to define what which plate will be what. The same was done for the backs. Okay, so here we can see again that there were two which were more different, and so one was decided to be, one would be the thick. Actually, no, this one was decided to be the thin. And why do we have the thin? We have 3 here, 4 here, which are the medium ones, and this one will be the thick one. I'm just a bit puzzled why this one you didn't do it a bit more, but just by looking at the graph. But so again, so it was based on the impedance again, so mode 2, mode 5, and using this as a guideline to control the graduation at different steps. So
in a moment, Claudia. I don't actually remember this quite as being that much difference between the 4 mediums. We did look at other factors, such as the actual frequencies of the modes, as well as the weight. So I mean, although the impedance is the best guideline on its own, like, you need to look at as many things as you can.
Okay.
So we're looking at their kind of, you know, the mode frequencies and the weight and various other things. So there were reasons why we took those decisions. Or in one case, it might be that one of the students went a bit beyond where we wanted them to go.
Okay.
But
this one, it was more like you stopped.
The logic of the tops.
This one it looks more like you stopped before. But there was
I don't remember one of them. Maybe I don't know. I don't think we had any of the medium plates that were that heavy. I think they actually were. I think this is a step before we finished.
Okay, so maybe one point is missing. Maybe 1 point is missing.
One of them was 99 grams, and the 1 or 2 were about 1.1. They were much closer to that when we finished.
Okay, so probably this is a graph. This was provided to me, and probably 1 point is missing. Okay.
Yes, one step.
Okay, so what is important for you to understand is the fact that the decisions were made using the vibratory behavior of the plates, and that's what is important to actually help in the guideline of graduating them. All thicknesses have been carefully recorded by the team in BELE. So everything is fully documented. Then when you have the plates, you need to assemble them. So same to minimize the influence of hand working. The necks were partially routed in order to make them as similar as possible. Then they did a very careful selection among a very large number of fingerboards. And again, using the impedance again, so measuring first mode of frequency, multiplying by the mass. Then next, along with glued fingerboards, were then crafted and systematically measured until all of them had the same impedance parameter value, mass times frequency. About the neck fitting, the neck set and the projection of the fingerboards over the bridge were also studied and done in the same way in all the violins. This value of the projection needs to be exactly the same in order to produce the same bridge pressure over the top plate in all of them. If this pressure changes, it would affect the loudness and the tonal quality. So this was carefully controlled as well, to be the same for every violin. Bridge, so bridge selection. So they used about 50 specimens supplied by Despio, and they were all measured to obtain the most similar 6 bridges in terms of impedance again, so mass times the rocking frequency. So here you can see you clamp the bridge feet, and then you give a little knock here in this area, record with a microphone or accelerometer or something like here. I think it's a little tiny microphone. And you can measure the first rocking frequency. And you multiply by the time of the bridge, and that gives you a Z number. And so they chose the 6 bridges, which were the closest as possible in terms of this parameter. Then the setup. So that was a difficult decision as well, is like, what do we do? Because to some extent, of course, if you use a thicker plate, you will probably not have the same setup as if you use a more like medium plate. And so it was a discussion, shall we set up all the violins the same, which means that maybe some violins could be disadvantaged, or shall we optimize the setup for each violin? But then if we do so, then we kind of thought that we would not be able to really to look at the effect of the thickness of the plate. So we finally decided to use the same setup, even if it's not what you would do in a normal practice.
Claudia, there's just one more detail there, but after the setup, I went through them and looked at them, and particularly with the ones with extreme plates, I just checked that by a small move, whether suddenly the sound might be transformed, that we might be grossly misrepresenting the capability of an instrument. But I didn't find that was the case, and I left the soundposts almost exactly as Fernando had set them.
Yeah. So this is Fernando, who is working in Roberto's workshop, and we did all the setting of the sound post adjustment. The strings, the Dario strings, as usual, thanks to Fantao. So they were all mounted with Kaplan strings. And so after a lot of work, we managed to have the 6 violins. And here you can see on this picture, there are more than 6. There are actually 12. So why 12? It's because we decided that the 6 violins, we know that if you actually make violins from, there's a lot of constraints, but made by the same people, they will probably be quite close to each other. And so we wanted to put this variability in terms of thickness in a larger variability, which could be done by choosing wood slightly differently, by doing slightly different adjustments, by graduating the plates in a different way. So we've asked 6 what we call external makers. So they're not the Bilbao violin, the Bilbao school violins, to actually build a violin. And we imposed some of the same constraints as the BELE violins, but some more freedom as well. So we imposed a constraint on the wood density. We asked them to choose the wood with the same density as for the Bilbao violins. And then they sent us the wood. So the wood was then CNC routed, the same way as the Bilbao violins. The scroll was CNC routed. We gave them as well the bridge from Despio, some fingerboards. I mean, there are plenty of things that were provided to them, but then they were free to actually set them up the way they wanted, of course, and to graduate the way they wanted. Okay, so for the graduation, there was no constraints. So that means that we have a set of another 6 violins which share some constraints and some similarities with the Bilbao violins, but providing a bit more variability in terms of construction choices and design. And we added as well 1 more violin, which was made by one of the external maker, but on a complete different model. It was a Plauden, based on the Plauden. And so to see how much like a complete different model, would that stick out in the group or not, because it's made by the same maker as another violin. So that was an interesting point as well, to throw an outlier in the group. So I'd like to thank Roberto, George, Paul, Ruth, and Francesco for having made a violin for that project.
And Jessica also.
And Jessica, yes, I was like, oh, that's not 6. Thanks. So of course, many measurements were performed at the different stages. So I talked about the model analysis of the plates to get the Z impedance. They were conducted not just after, they were conducted through different steps, like after CNC, after graduation, without and with base bar. And they were performed with two types of boundary conditions. So the first is the free, which is a standard way. Yeah. And so usually they are put on a silicone mesh, which is very lightweight. And then you measure, so same usual method, you hit with a hammer, you measure the vibration with a little accelerometer. And then the other way is something we have discussed a bit earlier this week, which is a method invented by George, which is called the pin edge method, because he thinks that basically that's closer boundary conditions to the fully assembled violin than the free plates. So the free plates is something which, of course, is very far from how the plates behave when they are assembled in a violin. And you can think that basically assembling the plates with ribs is closer to a pinned edge condition than to a free. And it does change indeed a lot, the modes and the frequencies. You have to think about the amount of hours it represents. It's 51 points for the backs. You have to tap each time between 3 and 5 times. It's 62 points for the tops. And then you have to do it at different stages for all the possible plates. And then for the finished instruments. So it's thousands and thousands of taps and hours of work to collect all these data. So here was like an intensive measurement sessions at the Bilbao workshop, but a lot has been done as well by Unai in Bilbao. So on the finished instrument, it's 113 points, and they did it for the closed box without sound post. And then some sound radiation measurements were made on the 12 finished instruments just before they were used in perceptual testing. A few graphs to show. So here are the measurements. So it's the average frequency response function over the 62 measurements, because I told you there were 62 points for the free plates. And this is for the 6 tops when they were just routed with a CNC routed. Okay, so before any graduation. And you can see that at low frequencies, they're really like lie on top of each other. But then unsurprisingly, when you arrive at around 1000 hertz and above, then any tiny differences can make a difference. And then you can see more differences in the high frequency, which was expected. You can expect to control with, you need a very, very high accuracy to be able to control at high frequency, but with wood, it would be almost impossible anyway because of local differences. That's after graduation. So now you can see that we have the 4 which are quite close. And then we have obviously 2 different ones, which is one being the pliant, one being the resistant. Okay, so we can see that the graduation has really spread the pliant and the resistant away from the medium ones. And the medium were they managed to keep the medium quite close. Though you can see getting more differences already at 400 hertz. That's for the 6 backs, just after being cut with CNC. So we see very similar patterns, very close at low frequency and starting to spread more around 1200 hertz. This is a measurement. I told you there were 51 points on the back to do the measurement. So that's an average over the 51 measurements. And at the 6 backs after graduation, we have here the medium ones, and then the pliant back, and then the resistant back. So again, there are some differences, and you can see that one is a bit more different than the 3 others for the medium backs. But clearly the differences are much, much, much smaller than they could be for deliberate differences, like for the pliant and the resistant back. These are measurements of the 2 bodies, just the corpora, so without neck and soundpost, with the 2 medium tops and backs. So the average FRF over the 113 measurements. And you can see that they look pretty similar up to 1,400. So just here, a bit of difference here, 2 dBs on the first or second mode. But otherwise, they are matching quite amazingly when you think it's 2 wooden structures with still some hand intervention. That's the sound radiation. These are the sound radiation for the 2 control violins. So I don't think you will ever see 2 radiation. I mean, if you look at them, especially if you have done quite a lot of radiation, you could easily think that the same violin measured at 2 different times. It's really amazing how the curves lie on top of each other. And to give you an idea of how otherwise they could differ, that's 2 different violins, with the red one being the medium top and back. So one of the 2 mediums that is here. Same red one, and the blue one is resistant top with a medium back. And you can definitely see that there are more differences with the peaks not being aligned as they are here. And with differences here, somewhere here, differences here. So definitely the medium violins are much alike than the other violins which were made to be different. However, when you look at these 2 plots, you can still feel that it's not so massively different. It was a bit to surprise. We could have thought it would be even more different compared to what has been done in terms of thicknesses. And so that shows that in terms of radiation, probably the arching is imposing quite a lot because it's not massive differences compared to what we could have expected when you look at the differences in weights of the plates. And then that will be my second talk. So I will not talk about this now. It will be my second talk. But basically, as I'm sure there will be some questions, I'd like to let Roberto, George, and Unai maybe talk about this. So I have a few slides that Unai you had made, to talk about contours, archings. So maybe you want to talk about this because that could be interesting to the group. So.
Like to point out that Unai did an enormous amount of the measurement work. I think he did more than me. But I sort of almost lived in Bilbao for a while. Started to feel like home.
Yes, you were the chief.
So the people in the restaurants and bars, they recognized me when I went in. Yeah,
so
it's a big chunk of our lives.
I think that it was a very intense project, but very interesting for the school and for us also, but not as easy as we thought in the beginning. And maybe we know in the future, if we do another one, we know really what to do and what not to do.
I think if we had to run the experiment again, we would have a lot of experience to help us get there quickly, good results. Yes. But we kind of knew it. We knew it at the time that was a part of the project was to test the viability of such a project. So Jim would like to talk, and thank you to Jim. He put in a ridiculous amount of work in sorting out my funding aspect of the project. Thank you, Jim, for that.
That's not what I was going to ask about. I was just going to ask Claudia a quick technical question about these slides. They flashed past a bit quickly, but the slide for the tops as routed and for the backs as routed, they look suspiciously similar. Are you sure they weren't they both had the green one standing out as different? Keep going back.
So that's the mid.
No, it's the as routed before the graduation. Keep going. Now this one has one plate at 2.6 kilohertz standing out with a high peak. Now just go to the one that says it's the backs. I think that's the same plot. That's to prove I'm awake.
Oh, yeah.
Yes, you are awake. Wow. Yes. Yes,
I actually think the backs were more similar than the tops.
Yes, I don't know what happened. I made up when I copied paste something from Unai's presentation. I just copied the wrong one. Yes, but I mean, okay, fair enough. Sorry for this.
Yeah, maybe in my presentation I made a mistake, but when we publish this kind of things and the results, maybe we will fix all of these things.
Oh yeah, yes, we will for sure. But then I took Unai had made a presentation which I wanted to simplify a bit for, and so maybe I just copied the thing twice. Yeah, obviously it is a mistake, but basically you actually have the same patterns for both the backs and the tops. But
I believe you. Because you don't even know whether these are in fact the tops or in fact the backs, do you? Hard to guess which one it is.
Oh, I'm sure George knows. Oh yes, no, we can know because basically 120. Ah yes, no, not so easy. We can't see enough because of the scale is too.
Yeah.
Yeah. So did you want to talk about this or not really? George and Unai.
Well, we had quite a lot of problems in the beginning with the construction around the edges of the seabelts and things. But that got more or less resolved later on.
There was a problem with the corner as well.
In theory, this idea of a scan and a digital workbench to sort of fix it good enough for working, it's not that easy. It takes quite a lot of experience for people to get the manipulations right. And overall, we could do with a whole new sort of technology for reverse engineering the distortion. It'd have to be a combination of advanced CAD and finite element modeling of some kind. But I think it will come. We need it, and the people with the expertise are there. It's just a matter of focusing a group of people with the right skills, and we could have it. And that then is an amazingly powerful tool because it allows you to basically work on models very close to how they might have been when they were actually originally made. And a great learning tool. I mean, to work on a plate or a scroll that's CNC cut is a very informative experience. Even if you think it's lazy or not good making practice, it's still you can still learn an awful lot about the shapes.
I don't know. Are there any questions about this aspect?
I have one question, if you can hear me.
Yeah.
Yeah, I wonder, those instruments are white and I guess you keep them at the same place and so on for some kind of time so that they will stabilize their humidity content and so on.
Yeah.
But you have done a lot of tests here. It's remarkable. But I wonder, have you been looking into what happens with the instruments at high and low humidity content in the air?
Yeah, this is a very interesting question, because one of the violins that worked perfectly and was one of the prefers in Spain, then when we traveled to Oberlin with those violins, this violin was not so well sounding. It changed a lot, and was the violin who has actually the pliant back. And maybe this could be a reason. The humidity changes more this violin than the others. I don't know if it's true or not, but yes, it could affect, sure.
But yeah, yes, I forgot to mention that the idea was to keep them unvarnished to avoid any other layer of complexity by, varnishing them, and how we do the varnish, how do we control the application of the varnish and everything. So we thought, let's keep them white, which avoids another source of variability.
I guess there's possibilities for more measurements and tests in the future with them. Are they? Yeah. So they are kept as experimental instruments, then they are not finished and sold?
No. So the 6 external violins, what we call external violins, yes, they have been varnished and sold. We can't expect makers to take part in the project and make a violin for free, So at the end, they had to sell it. That's normal. But the 6 BELE violins, which were funded by Erasmus Plus, are property of the school, and that is that part of the conclusion of my second talk is a pedagogical tool, and should be used as
a major problem with the morale project is the fact that we don't even know where those violins are now. Do they still exist? Have they been burnt? Have they been varnished and sold? Are they in a cupboard somewhere in Stockholm? So the fact is that they're there in the school. People could visit and play them, and that, the actual experience of playing those violins and with the knowledge of how they're constructed is extremely educational.
Claudia, could you tell us again for correcting the deformations in the archings? Did you interpolate it in the CAD software or something, or did you do it by? I didn't quite get that. How you did that?
Ask the experts. Yes, George, Roberto, Unai, can you answer this?
In fact, a NURB surface was created in Rhinoceros, and it wasn't really completely, it wasn't altogether satisfactory, shall we say? But it's not that far from the original.
So how did you end up doing it?
Okay, you can see them for real.
Yes. Yeah, here there are 4 of them in the school, and the others 2. And maybe they are available for anybody who wants to investigate with them.
We were supposed to work on them again this week for real, but it hadn't been possible.
Yeah, if we could travel.
Yeah, there were plenty of things we wanted to do with them this week, but yeah.
Well, I have
But I mean, Hans, has George answered your question?
Not quite. He said that they created a NURBS surface in Rhino, but was that what was used in the end?
Yes, but after that surface was created, we then had to go back and modify it quite a lot. So you can do, as Francesco showed you, you can take your mathematical model and then you can compare that against, the original and see what you've done. And in the end, we actually retain quite a lot of the asymmetry of the original. which I don't know, we're not, that wouldn't be my choice as a general working method, but in terms of the experiment, the most important thing was that they were all alike as possible.
Mm-hmm. Okay, thanks.
So, I don't really want to say all the details and my gripes about it, because there are many things about that stage of the process that I'm not happy about. But I think in the end, it wasn't too damaging to the experiment. It's just I don't want to. No, I don't want to say what I don't want to say. It's like you know, a good interview with a politician. You can make them tell you the thing they don't want to say.
Yeah.
But it is difficult, and I think in the light of the experience of this project, we now know a lot better how to go about those things. So we've learned for sure.
Right.
I'll ask one more question before you move on. I can guess the answer to this, but you didn't include it in your slideshow. I presume you have bridge admittances on all
Yes.
12 of the instruments?
Yes.
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 Now, Claudia,
Yes.
did you try stirring that into the work that you did when you were in Cambridge? Because you should be able to predict whether people will be able to tell them apart, because you found the just noticeable difference for moving modes around. So you should be able to make a prediction about which ones can be distinguished and not based on that work. And it'd be very interesting to know if that bears out in practice.
Yes, that's again the conclusion of my second talk, is there's still lots of data to analyze and to deal with. Yeah. But yeah, indeed.
I think by and large, though, these structural things worked out as we expected, pretty much. But when it comes to perception, that's just so much more difficult.
Yeah, but we do have some ideas because of, say, Claudia's project from what, 12 years ago now, 15 years ago, whenever it was that you did that work.
12,
it's we can. You can definitely make some predictions of things that should definitely be distinguishable.
Yes,
there may be things which on that basis are not distinguished, but other things make them distinguishable. But it should be that you can, you'd expect the extremes to be different enough, maybe, to be distinguished just based on the things that you explored.
Well, especially that there is an effect, as we could see in the radiation measurement, that there is an effect on the B1 plus and B1 minus, and this was clearly investigated in
Absolutely.
our study.
But you have a definite measure for that in the bank somewhere, don't you, of how many, what fraction of a semitone you have to move something by in order for it to be perceptible, and how much you change the damping by. You probably didn't get big differences in the damping, but the parameters will be interesting to see.
I think
Jesus has a question.
Yeah.
Hi. Speak, Jesus. Habla.
Oh, thank you. Claudia, can we consider that the arcing profile of your violins is the better controlled variable in the 12 violins? Yes?
Yes.
So then can we detect what part of the response remaining constant if we maintain the arcing profile in some violins and all the other variables is moving, it's changing? It was clear? I asked my question? No?
No.
The arcing profile of your violins is the better controlled variable in your violins?
It was controlled because that was done by CNC.
well, we can say that all the violins has the same arcing profile.
Yeah.
Yeah? So
as near as it's possible.
then maybe your violins are the violins with the better controlled arcing profile.
Yeah.
No?
Yeah.
Can we conclude something about what happens with violins with the same arcing profile with several other variables changing? It was.
But that's the goal.
The arcing profile is the goal of
No. The goal of the project is for a given arcing profile, what happens if you change the thickness?
Yes, we're trying to limit it to one parameter. Because if you change the thickness and the arching, you don't know where to attribute the differences. So the idea is to change one parameter and make that difference so big that it really must be, the difference must be due to that.
Okay, I understand. Thank you.
And we did, Colin did some modeling of that in order to give us some sense of what the scale of difference would need to be. Yet we're still within range of things that people actually do. So although they were extreme, they were not something that you would never find in other instruments made by people in all seriousness.
Yes, because that's quite important, you know, and that's always a bit what is difficult, I think, in musical acoustics is like, you know, as a researcher, you're always told start with big differences, you know. But the problem in our field, if you start with too big differences, then the instruments become so problematic that when you ask players to play it, they say, well, that's crap, you know, it's so bad that they don't even want to play, they don't even want to evaluate, okay? So you still have to make as big as possible, but staying within a certain range that will be acceptable by players. And to find this, you know, limit where it's kind of extreme, but not too extreme, so players still will enjoy playing it, or at least not complain too much, is quite difficult.
Could I ask something? Did you? How did your measurements and dependence on frequencies depend on thickness? If there were thin plates, you'd expect everything, of course, to change according to the thickness. If arching is important, you no longer get such a strong dependence because the arching is dominating. This is particularly in the low frequency modes. Have you got some plots of the change in frequency of the individual modes as a function of frequency?
No, not yet.
Do you mean
sorry, as a function of thickness? I do apologize.
Yeah, no, I understood.
Yes, yes, we measured them at lots of different stages. So
but do you have?
There's so much data, Colin.
We don't have a plot just to present right now.
Because I would certainly be interested in that, because it tells you whether or not, I mean, if you don't get something that's proportional to the thickness in some sort of way, it's telling you that the arching is important. And
yes, we agree, because there is a certain similarity between all 6 instruments in spite of the differences. But you know, those plots that just Claudia showed you of the impedance against plate weights, I mean, that is telling you that information, because since the material is nominally the same, the plate weight is an indicator of the thickness. So the actual graduation thicknesses of the medium plates were very, very close.
Yeah.
But actually,
so in a sense, that information is there.
Colin is right. It would be really good to see individually mode 2 and mode 5 against thickness, because the whole point of Evans' number is that mode 2 should be a bending mode and mode 5 is more like a stretching mode. So his combination is precisely intended to combine these two things, and looking at the two separate trends will be very interesting.
One interesting thing about the model is it was actually quite difficult to get that the ratio of 2 to 5 high enough, or high as I might on other models. So you know, particularly I think the backs, you know, it was hard to get them. Some of them I think maybe didn't get above 2.
Yeah,
I forget the exact numbers, but
I mean,
but normally I get about 3 or a bit more.
You mean 2.3?
Yes, we could easily, yeah, 2.3. We could easily produce those plots. Yes.
Yeah.
Maybe they exist already.
It'd be quite interesting to see.
You just tell us what you want and we'll do it for you.
Yeah.
We just have to compile all the data, and there is so much to do.
You have done a great job, fantastic job, and there's a lot of data, and it's a bit early, I guess, to conclude. But still, I wonder, what did you take home, or what is your impression from the
Wait. Anders, there is a second talk now. Let's wait.
Okay, sorry. Okay.